Hello everybody, it's Professor Fiore. What's on tap today? Why, it's nothing more than common base lag network analysis. And the crowd goes crazy. Common base amplifier lag network analysis. Common base amplifier using a little BJT, a very common 2N3904, and we want to figure out what's the high frequency performance of this amplifier. What is the F2? Where does the system gain start to drop off 3 dB on the high end? All right, so the first thing we want to do is look at the DC analysis here, and I'm going to go through this kind of quick. If this sounds a little confusing to you, then I suggest you go back and look at some of the DC bias videos, or possibly the amplifier videos, the early amplifier videos on common base. But I just want to get through this so we have a basis so we can do our lag network analysis appropriately. In any case, so this is a split positive-negative bipolar power supply emitter bias configuration. So the base is wired right to ground. We have an emitter resistor here at 46K, 10 volt negative power supply on the emitter. So you're going to lose your 7/10. Don't worry, eventually you'll get them all back, but you're going to lose that 7/10. So the emitter is sitting around minus 0.7, meaning we'll have about 9.3 volts sitting across the 46K. That's going to give us a smidge more than 2 mils. You put that through the 50K, that'll be about 10 volts. So from the 15 volt source, we're looking at around 5 volts-ish at the collector. Now we're going to need that in a little bit. You're going to see why. But before we go any further, right, the R prime on this, always the constant 26 millivolts divided by the emitter current. So 26 millivolts divided by this slightly more than 0.2 mils will get us 129 ohms. All right. Okie doke. So let's go up and do a little DC analysis. Our usual table of results. I do like the way Tina TI does this. You get all of the things at once, just bonk, data dump. So here we go, looking at the emitter current right through the emitter resistor, 204 microamps. Looking pretty good, right? The drop across RE, 9.3 and change volts. That's looking good. You know, the pin 3 over here, which is the collector, 4.929, virtually 5 volts as we expected. So this is all looking pretty good, right? No big deal there. Now, we could take the difference between these two currents, the emitter and the collector currents. That's the base current, right? Which you can see is going to be, 2.6-ish or something like that, microamps. So if we divide that into the collector current, we'll get a beta. Beta turns out to be around 77. So not a super high beta. We don't really need beta the way we would if this was a, let's say, a common emitter configuration, as we'll see. Remember, the big deal about a common base amplifier, it's kind of like a common gate JFET amplifier, is that they're non-inverting. They get voltage gain. There's really no current gain. They get voltage gain. They have a small input impedance. Small input impedance usually translates into good high-frequency performance. And if you think of this equation, right, your critical frequency is 1 over 2 pi RC. If you have a very small value of R and a very small value of C, you're going to get a very big value of F sub C, right? Just kind of goes basic algebra. Now, having said that, the question is, hey, caps, what do we have for caps? Have to remind you, this is a non-inverting amplifier, so there's no Miller effect. That's another big reason why this thing tends to have good high frequency performance. I mean, it's always possible to design an amplifier that, using a common base, let's say, that has really lousy high frequency performance. If you don't know what you're doing, you just start throwing stuff out there. Yeah, you can make something with a lousy high frequency performance, but it has the potential, let's put it that way, right? It has the potential to have good high frequency performance. In any case, right? So here's our circuit. Now, what we need to do is find out, okay, what the capacitor values are. We're going to take a look at a data sheet in just a sec. I would probably also like to know, just for the sake of the simulation, to make sure we have a good sanity check here, kind of figure out what the gain and so forth would be. All right. So in a case like that, the gain for this is essentially your load, right? RC or RL, whatever you want to call that in the AC case, divided by the R prime value. So you've got an RC of 50K in parallel to an R load of 5K, 10-to-1 ratio. So you're going to get, a little over a 10% drop there. But 50K in parallel with 5K is going to get you 4.545 repeating K, right? So about 4.5K. So like I said, about a 10% reduction there. Now you take that value, the 4.54K, and you divide it by 129 ohms, and you get a gain of 35.2. That's the gain from the emitter to the load. We are going to lose some signal out here, though. And of course, you look at a 50 ohm and you think, well, what's to lose? It's only 50 ohms. But again, common base, low input impedance. In fact, the input into the emitter is just equal to R prime E. In other words, you got 129 ohms. So the Z into this thing is going to be 129 in parallel with this biasing resistor of 46K, which is basically 129 ohms, right? Now you got a divider between 129 and the 50 ohm. Well, now, 50 ohms is not so small anymore compared to that, right? It's, it's a factor of about 2.5. So you're going to lose nearly 30% of your signal, 25% of your signal in that region. In other words, only around 0.72, right, 72% of the signal that's coming from the generator is actually going to get to the emitter and is going to get that gain that we calculated of 35.2. So if you multiply that out, 35.2 times 0.72, you get a gain of 25.4, which is 28.1 dB. And as you might have guessed, I've done this already and wrote down the values. Okay, so we can do a simulation on that. Hopefully we'll come up with a gain, around 28 dB. Now we have to look at the capacitors and so forth on here. So what do we do, right? If we look at a simplification of this, an equivalent circuit, right, we would take the coupling caps and short them. I mean, they're a short for mid-band, so they're going to be a short at anything higher. Power supplies, we short those, replace them with their ideal internal resistance, so that's a short. So we see RE going to ground here. We see RC, just mentally flip that down because that's ground. Well, I have ground above you, right? You want ground down here. So we'd have RC out here. These two would end up in parallel, as would these, because of course your VGen would be replaced with its ideal internal resistance of a short. So you got a 50, you got a 46, you've got the Z in to the emitter, which is only 129, right? So you're going to have 129 in parallel with the 50, which is going to give us less than 50, obviously. It's a pretty small value. Out here, we have the roughly 4.5K that we already mentioned, but what about the capacitances? Right, so we have a base collector capacitance out here, a base collector capacitance out here, and a base emitter capacitance out here. All right, of course, the bridging capacitor, the collector emitter, is small enough to ignore. And again, not to beat this to death, but it's not an amplifier that inverts, so there's no Miller effect. We wouldn't have to worry about that anyway as far as Miller multiplication, right? That's one of the things that really sort of stomps on the high frequency performance of a common emitter amplifier. All right. Okay, where do we get the nice accurate values for the caps? Well, the best we can do is to get a graph from the manufacturer. Now you can just look up on a data sheet and, it'll tell you typically this capacitance is so many picofarads. But those are usually worst cases, or they're at an extreme of bias. So I grabbed a graph from the manufacturer's data sheet. And the first thing I want to point out here is that typically they don't give you like CBE, which is what we want. They give us something by another name, CIBO, COBO. Well, CI is input. This is base configuration with the output open. So technically, this is actually, if I go back to this original circuit, right? If you imagine this is the measurement circuit, if this is open, then what you're looking at here is an input capacitance with whatever this capacitance is in series with this capacitance, right? Because this is all open, this is all gone. Well, this is really, really tiny. So, caps in series add up like, resistors in parallel do. So that really tiny capacitor on the collector emitter basically makes this thing disappear. So CIBO is just about equal to the base emitter capacitance, and a similar thing happens here on the output end. So we can approximate. We can say that the base emitter is basically equal to CIBO, and the base collector is basically equal to COBO. So you can look up on the data sheet, right? So on Semi, on their data sheet, it gives you these values, 4 picofarads and 8 picofarads for output and input. But those are max values. So if you're trying to be really conservative about your computation, you could use those. But if you want something a little bit more accurate, don't use them. Instead, find out what your DC bias is, which we know, we just checked out the VCE is 5 volts DC, all right? Okay, not exactly, but pretty close, right? So what I do is I look up this voltage and then see what the appropriate capacitance is. Easy peasy, right? So in our case, we go 5 volts. So this is a logarithmic axis. So this is 1, 2, 3, 4, and 5. And as I come up, you can see OBO. COBO is about 2 picofarads. All right. And then if I were to continue up, we're going to estimate CIBO. I call it 2.8. All right. So there is a little bit of fuzz on that. But again, we do what we can, right? Okay. So I'm going to use COBO as 2 pico. CIBO is 2.8 pico. Then given the approximations, we'll just say CBE is 2.8 picofarads and CBC, right, the output end, is 2 picofarads, right? So we got 2.8 and 2, off we go, all right? So go back to our equivalence circuit, and there we go. There's CBE at 2.8, there's CB at 2 picofarads. Now, so I put this down here just as a reminder of what we had. Primarily, we needed the Z in, which is 129, okay? So that 129 is sitting out here. So you got 129 in parallel at 46K in parallel at 50 ohms. That's the input resistance. The capacitance is this 2.8 pico. On the output end, we have the 50 and the 5K, right? Around 4.5K. You got 2 pico for this capacitance. The other resistance we have out here is the internal resistance of the current source, right? The IC current source. But given these values, I got a 5K out here, which is really going to be the dominating element. That's big enough to ignore, right? This internal value is probably hundreds of K ohms, if not more. So comparatively, we can just say, all right, we got the 5 and the 50, and we'll call it. Now all I have to do is just sort of grind this through my standard critical frequency formula. Get that out. And here we go, right? So my input lag, 2.8 picofarads. My output lag, 2 picofarads. Z in, 129 ohms. The input lag is 129 in parallel with 50, which gives us 36. So you plug that into your formula with the 2.8, and you get 1.58 gigahertz. Well, good luck with that. That's a crazy number. The FT, which is the transition frequency for beta on a 3904, is something like, if I remember correctly, like 350 megahertz. That's where beta falls to 1. So do you honestly think you're going to get, 1.6 gigahertz out of this? Heck no. This is just what your computation is giving you. You can't, the model is the model, and we kind of run with that. Turns out this is not going to be a problem, as you'll see in just a sec, but that's what the numbers work out to. Now we move out to the output, and we take our 2 resistors, right, 4.545 K ohms, 2 picofarads, run that through, same formula, we get 17.5 megahertz. All right, that's a little bit more sane of a number. And this is typically what would happen, because you have this crazy small input resistance on the input, really tiny capacitance. There's no Miller effect, so you get huge values for your input frequency. you get more reasonable values at the output. You know, unless you're using some extremely small values out here for these resistors, you're going to get something a little bit more, you know, in the range of sanity. 17.5 megahertz is, yeah, that's believable. So let's go over to our circuit and see what we get. All right, so let's do an AC analysis here. Let's see, that all looks good. Okay, so first things first, I got to find the gain because we were expecting a gain of around 28 dB, and we're getting 27.75. Okay, 27 and 3/4. All right, so that looks good. The gain is looking good. So 27 and 3/4. So we're gonna have to drop 3 dB from that. In other words, 24 and 3/4. That's our 3 dB down point, which will be the system F2. All right. Dun, da, 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 dun, da, dun, da, da. Oh, it Bert bleat. Going the right direction. Okay, well, so we're not exactly where I want to be. That's a little high. That's a little beyond. Oh, look at that. So on the one hand, maybe I can kind of squeeze it over here a little bit. Yeah, I don't think we're going to do any better than that. All right, so call it 16.6. 16.6 megahertz. All right, maybe it's a smidge more, but fine, 16.6 meg. So we had computed, what did we compute? I took it all over here. All right, so we had computed a value of 17.5. Well, that's not too bad, 16.6 versus 17.5. Now we are using estimates, like I said, squinting at the graph for the capacitors and so forth. And that's looking pretty good. All right, so the last thing is, how do we check the 1.58? Well, we don't, right? We don't do that. It's a crazy number. Don't even worry about it. Unfortunately, there's no easy way to do a translation. You know, in the lead network analysis and some of the other lag network videos I've done, we can do a frequency translation because there happens to be one component that in isolation, right, can be used to set the critical frequency. So, you know, for example, if you're doing a lead, you could just take C in and increase it or decrease it depending on whether you wanted to make, you know, this other capacitor, you know, critical, right? Or the other way around, right? So it's easy to do. In the case of, you know, maybe if this was a common emitter amplifier, you would have a relatively high input impedance and you could play around with the generator impedance. Now you could bring that up, which would, of course, by increasing R, would translate FC down. You could make it dominant that way. And that doesn't really affect much else in the circuit. But here you're kind of stuck because you could make Rgen huge and it's not really going to impact the overall frequency response, right? The input critical frequency, because you've got this small Z in over here. So the end result is, you know, you make this huge, well, you can only do a very, very modest change in R and the R in, right? This thing over here, and consequently a very, very small change over here. So you're, like I said, you're kind of stuck. Now you could put big capacitors out here. You know, you could just say, oh, I'm going to add a 1 nanofarad capacitor. All right, you know, you could do that and you would come up with an appropriate frequency. And that might be perfectly valid if for some reason you had a really large input capacitance, some cabling or something that you had to deal with. But, you know, otherwise you're not really sort of cross-checking the model. You're really just checking this other big external capacitance. So, you know, we just kind of have to take this as, well, normally with typical circuits, you don't run into that issue. This is the one that's going to be the dominant network, right? And to be honest, if you were really looking, like I said, to get frequencies up here, you wouldn't be using a 3904. It's just not made to do that, right? It's not designed, the transistor is not designed to be working up at those frequencies, all right? Okay, so I think that pretty well covers it. If you have any questions, I think you know what to do. Put them down in the comments, and we'll see you next time. Take care.